Hi everyone, I'm Murphy. I'm a graduate student at the University of Waterloo, and I do this, thank you. I am actually doing my PhD in formal methods right now, and so I thought I would come and talk to you about it today. So let's get started. By the way, you can tweet me questions at my terrible Twitter handle that I refuse to change, and I will try and answer them after the talk, or come find me during the break. Let's get started. So we're going to go over an introduction to what formal methods are, and also a little bit of formal logic, which I promise won't be that bad. And then we're going to talk about SMT Solvers, which are a really cool new technology. And I'm going to show you actually the Z3 solver from Microsoft Research, which I've contributed code to. We're also going to learn a little bit about Symbolic Execution, which is a cool application of formal methods. And we're going to see a little bit of the KLEE virtual machine. Both of these tools are freely available and open source. You can download them today and start using them right away. And then we're going to talk about a little bit of the future of formal methods and some of my research directions. This should be a lot of fun, so let's get started. So formal methods are very simply techniques based on mathematics and logic. And we can use these to develop systems, specify them, and verify that they're doing the right thing. And this allows us to either prove properties of programs that we're interested in, like safety properties or other correctness properties, or to find counterexamples, which could mean a bug or a security vulnerability. And these systems are really, really important for software reliability and software testing, and especially in safety-critical and security-critical software. Formal methods, of course, aren't infallible. Proof systems have their limits. You can't prove safety properties that you aren't trying to prove, so they're not magic oracles from which you will get magic proofs of, oh, everything is fine if you don't know what to ask for. And of course, there are some things that you can't prove at all, but formal methods are really useful in complement with other software engineering best practices like testing and code reviews. So some simple examples of formal methods, well, an easy one is actually type systems. If you've ever used a strongly typed language, the type system is actually a way of proving that your programs are only going to use data in particular ways defined by the type system. So the compiler will do something like automatic proof checking to see that your program hasn't committed any type errors. And a type error is essentially a counterexample that's found during this proof. Hardware designs like microprocessors are formally verified to establish correctness. This happens to be a terrible example this week because of what was found out earlier, but maybe we will learn better ways to prove these properties in the future and be able to automatically establish security properties as well as important correctness ones. On a hopefully lighter note, Windows device driver validation, which I don't think there have been any big driver bugs lately, fingers crossed, that also uses a theorem prover to verify safety properties of Windows drivers so that they don't perform memory accesses out of bounds. And this automatically runs before the drivers are validated. So this sounds kind of high level and advanced, and I really don't think it should be presented that way. It shouldn't really be that scary and unapproachable. You know, I don't want people to think that they need advanced degrees to approach this field because it should be accessible. I want to promote applications of formal methods that anyone can get right into and start benefiting from. So we can even introduce basic ideas of formal logic without actually really needing that much theory. So we're going to see two tools today that you can download right away and start using to prove theorems and do cool stuff with formal methods. But first, a brief tour of formal logic. This is not that bad, I promise. So Boolean logic, which you might be familiar with from programming languages like C and C++, variables can be true or false, and that's it. And there are some simple operations we can perform on Boolean variables like logical and, or, and not, as well as a few others that are more useful in a theorem-provey context like implication, and if and only if, exclusive or, and so on. And so these are just the familiar operators that you may have seen before. And so we can start talking about now putting these operators together with variables and constants to make formulas. So there's a simple formula given at the bottom that doesn't really mean much, but just gives you an idea of what it could look like. So now we have a formula, we have some variables in it. And now if we have a formula with variables, well, natural question is, does it have any solutions? Well, in this case, what we mean by a solution is a way to put different values into the variables so we can replace each variable with true or false and try to evaluate the formula and find out if the whole formula is true or not. And this leads us to a really important question called Boolean Satisfiability. So we say that a formula is satisfiable if it's possible to assign either true or false to each variable and make the whole formula true. If a formula is always true, no matter how we assign the variables, the formula is called valid. And if there's no way to make the formula true, no matter how the variables are assigned, the formula is called unsatisfiable. And these are terms that come up a lot in the context of theorem proving and SMT solving, and so it's a bit important to just have seen this before to be familiar with the words. So how do we solve satisfiability? Well, we can use something called a satisfiability solver or a SAT solver. These algorithms are not new. They've actually been around since about the 1950s. And so SAT solvers, well, the easiest way to solve SAT is brute force. So if we have n number of variables, we can guess true or false in every possible combination and try 2 to the n different ways to solve the formula and see which one comes up to true. This takes exponential time, and that's pretty bad. And if we actually did it that way, I wouldn't be giving this talk because this field wouldn't exist. Fortunately, practical solvers often perform a lot better than that because they're quite clever. We're not necessarily going to get into that because this is not that talk, and it's an entire field of research. But SAT solvers are really, really cool and quite fast. And they're used in applications like hardware verification. Oh, here's an interesting one. Software package dependency resolution. If you've ever installed an Eclipse plugin, you have benefited from a SAT solver. It uses a program called Sat4j to resolve dependencies when you're installing Eclipse packages. As well, scheduling and logistics companies use SAT solvers to solve TSP and Hamiltonian path and other problems like that. So SAT solvers are great, but then something a lot better came along called SMT solvers. And these are like SAT solvers, which are a little bit more relevant, I feel, for things like programming and software. So some problems are a lot more naturally expressed using things that aren't Booleans. So you might want to talk about a program that does math on integers, or a program that does strings, or floating point numbers. These are sometimes hard to encode with Booleans, or sometimes the encoding is not trivial. Sometimes they're impossible to encode with Booleans. And so you need something stronger than a SAT solver. And so we get into SMT solvers, which combine Boolean logic, which we've seen, with one or more theories over different domains. And a theory is just a way of saying, well, we're going to think about a domain like integers. We can have theory of integers, theory of floating point, theory of bit vectors, theory of string, and they combine different theories and let you perform automated reasoning and try to prove theorems with them. Hence the acronym SMT, which stands for Satisfiability Modulo Theories. And these let us, they're great because they let us perform automated reasoning tasks over really powerful logical theories that are relevant to programming languages. So instead of having to figure out in encoding to Booleans, for example, if you're trying to prove something about your floating point arithmetic program, you can just use floating point operators directly. You don't have to worry about how that conversion needs to be done. Speaking of SMT solvers, here's one now. So introducing the Z3 Theorem Prover, which has actually been around for a while. So this is an SMT solver that is developed and published by Microsoft Research. It's actually an open source package. It was open sourced under the MIT license a couple of years ago, and you can download the latest version from their GitHub page there. You can also install it from most package managers, and if you have the pip module for Python, you can run pip install Z3 solver. You will get the latest version of Z3 and the Python bindings, so you can fire it up in your Python IDE or REPL and start mashing formulas from there. And the documentation on all of this is really great, by the way. And Z3 is really nice because it's very, very general purpose. It supports lots and lots of theory. So it's not a specialized solver for any one type of logic, but instead it can solve a whole bunch of stuff. So it is a really great way to get started with SMT. So Z3 supports arithmetic over integers and real numbers. It supports reasoning about strings like you might see in JavaScript or Python. By the way, I contributed the string solver code to Z3. I am actually a Z3 contributor. So if you are reasoning about strings, please let me know. I would love to support your application. Z3 can also reason about bit vectors and arrays and floating point arithmetic, which lets you model programs in low-level languages like C. And it can also do abstract data types. You can reason about data structures in standard ML, for example. Z3 also has API bindings for languages like Python, Java, C#, and C++. So it's really easy to integrate with different libraries and programming languages. If you need a constraint solver or a theorem prover in your project for whatever reason, you can grab these Z3 API bindings and integrate it and start using it right away. So we'll see. on the next slide, actually, an example of that. So yeah, as I mentioned, Z3 will take an input formula and it decides whether the formula is satisfiable or not. If it is satisfiable, Z3 can find a solution to the variables and tell you what that solution is, which is actually kind of nice because not all SMT solvers do that necessarily. As a brief note, if you want to check if a property is always true, you negate it and check unsatisfiability, because as we saw, validity and unsatisfiability are kind of the duals of each other. And in this case, if a property is unsatisfiable, it can also mean there is no counterexample. We'll see another application of this in a bit. But let's see a simple example, actually, of proving an invariant with Z3. So this is some Python code. You could type this into Python right now if you had the Z3 libraries and check this proof for yourself. So we import the Z3 library and we create 2-bit vectors. So these are essentially 32-bit binary integers named x and y. And then we instantiate the solver, and we're going to add 2 assertions to the solver. The first one is that the variable y is equal to the variable x shifted to the left by 3. And the second assertion is the negation of the property y is equal to x multiplied by 8. So essentially, we're trying to check the validity of equivalence between these 2 expressions, that left shift by 3 is going to be equivalent to multiplication by 8 for these terms. And if we ask Z3 to check this property, it will say unsat. This means that Z3 proved there is no counterexample. So in this case, the property is actually valid. To see an example where we do find a counterexample, we can look at arithmetic right shift. Which I remember having problems with when I learned C, because I thought, oh, it's the inverse of left shift, so it must be like division. It's kind of not, and we can prove that it isn't. So we can set up a similar proof here where we show that x shifted right by 3 is not equivalent to x divided by 8. And if we check it, Z3 says this is satisfiable. So oops, we found a counterexample. And we can actually ask Z3 for the model, which is to say the solution, and it will tell us that the following integers actually provide a counterexample. So we can plug those into the original formula and find out that this ends up being a problem. So in this case, we could actually take this counterexample if we were making, for example, an optimizing compiler and turn this into a test case. And now we know this is a problem for us where this conversion isn't valid. In another case, this could be used to, you could fix a bug in the program or do any number of things with these counterexamples. So now we're going to look at an interesting application of SMT solvers called symbolic execution. And this is another really, really cool idea for software testing where SMT solvers really provide a unique benefit. So an idea when you're testing software is you might want to test a lot of different program paths. In fact, as many as possible if you want. And another idea is to test inputs that are very likely to expose bugs in the code. So suppose we see a line like y equals 100 over x. Well, could x ever be 0 on that line? Could that line ever actually be reached? What if x depends on other conditions somewhere else in the program, and the value of x might be reached through a very roundabout way? How do we write a test case that could expose this bug? The challenge is to find the inputs that actually make x have the value of 0. And so symbolic execution uses formal methods to test programs and create tests that uncover real bugs like this one. And it's a way to explore different paths in the program in a very regimented and logical way. So what do we mean by symbolic? Well, the CPU, when you ask it to do a simple arithmetic operation like 2 plus 2, it knows how to do that operation because it's doing operations on numbers. This is math on so-called concrete values. But if the CPU is asked to do 2 plus x, and it doesn't know the value of x, it can't do that operation. And in this case, x is called a symbolic value, and this becomes a symbolic computation. Now, if we had a way of carrying around these symbolic values and simulating these operations without getting the CPU involved, we could maybe use a theorem prover to solve for the symbolic values and make them concrete. And what we're doing there is essentially using a program like Z3 to evaluate a bunch of logical formulas and find out whether a particular value can end up activating a certain program path or not. So these symbolic values in cases might depend on previous conditionals, it might depend on loops, and the idea is we want to explore different program paths in the sense that we want to keep these dependencies in count as Boolean constraints that say, first I went this way, then I went that way, and we want to see, given that that happened, can we make this thing true or not? And that's what constraint solvers are really great at. And so there's a program that can do this for us, and it's called the KLEE virtual machine. KLEE is a symbolic execution engine for C and C++ programs. It's an open source tool. You can download it at their website, klee.github.io. There's also a Docker image, which I haven't used myself, but it sounds really good because it means you don't have to compile KLEE, and I've heard that's a bit of a pain. KLEE runs on top of the LLVM compiler toolkit and virtual machine. So if you're familiar with that, you may be able to get started with it more quickly. And KLEE also uses Z3 as a backend. So in this case, you don't interact with the theorem prover directly. You just you invoke it indirectly through your use of KLEE. So KLEE is a bit complicated, so this is a bit of a high-level introduction, so I would recommend checking out the documentation, but just to give you a taste. The idea is that when you want to test some code, you augment it with these special functions. So in this case, we have a function called KLEE make symbolic, and there's another function called KLEE assert. KLEE will actually link your program with a special library where it knows how to use these functions and turn them into symbolic constants and be able to do this evaluation. So essentially, you're telling KLEE where to get involved in the program. So you're telling it what variables you want to test, what you want to make symbolic, and what conditions you want to check while your program is being tested. You compile it to LLVM bitcode and run KLEE directly on that file. And KLEE will call the solver as it works. So again, you don't need to directly touch the solver if you don't want to do that. KLEE will then produce a test case for every program path that gets explored. And this is really cool because it will explore your program automatically and look for things like crashes and incorrect memory accesses and assertion failures that you ask for it to check. And every time it finds one of these crashes, it will keep a note of where it explored and try not to do that again. So in this case, it's actually kind of smart about how it explores your program. It tries to expose new behavior with every program path. There are some properties you might want to test, like reachability, for example. In this case, you can just do the classic assert false, except you do KLEE assert false at the proper program point. And this is a neat trick to see, can this line of code ever actually be reached or not? So just to show what this would look like in the context of a very simple program, there's just a call to KLEE make symbolic, and you pass it the address of a variable and its size and so on, and the interface is absolutely terrible, but that's what KLEE expects, unfortunately. Hopefully this will be better in future versions where this might be annotated automatically, but for now. And there is a way to disable these annotations in production code, so you can leave them in when you compile your release binary. But that's actually all you need to do, is just add this one line and compile with the KLEE front end to LLVM and run your code, and that's it. And KLEE will do its job automatically. So as I mentioned, KLEE will try to make a test case for every unique program path explored. That includes things like different branches of conditionals, different loop counts, and so on. And it tries not to crash the same way twice. So if it does find bugs, it will try and find different bugs in as many different places as possible. The test files can also be converted and replayed, so you can see the KLEE documentation for more information. Just to wrap up with some brief applications of formal methods that might be coming up in the future. So historically, there's been a bit of a contest between solver writers, and everyone is trying to make the most powerful tool, the fastest tool. Everyone's trying to beat out everyone else, and the solvers are getting better and better. But at the same time, there aren't a lot of people developing really good accessible applications that a lot of people want to use, and maybe I want to do something about that. So my hope is that, we want to get these tools into everyone's hands, and we want to make people able to benefit from these really cool ideas, because I think they're really cool, and get them into practical tools and analyzers that everyone can use. And the end goal is to make this really a part of regular software development and testing. So if all of the developers can benefit from it, then this will really be, hopefully, a really great thing for the software ecosystem. Of course, it's not going to replace other techniques, but it'll hopefully be useful to everyone. So that's it. This is a bit of a, I know this is a bit different from the other talks today, but I'm really glad that I got to present this anyway. So here are the URLs for those tools. You can go and grab them and download them right now, and start start messing with theorem proving today, because it's really cool, and I really hope that you'll be able to look into this more, because there are so many cool research topics and research questions that you can explore, and even for your own projects. If you need a constraint solver or a theorem prover or some way to do dependency resolution, you can go and grab these and start using them right now. So yeah, send me your questions at my Twitter handle, and that's it. Thank you very much.